Welcome back. It's lesson 9.3 today. We're going to be looking at integrating trig functions. So, just like how we learned the derivatives last day, you need to now be able to go backwards. And so once again, the integral of cos is just sine, and don't forget an indefinite integral has the plus c. The integral of sine then of course is negative cosine. The integral of secant squared is tan, cosecant squared is negative cotangent, and these are the ones you should know. Secant tan becomes secant, and cosecant cotangent becomes negative cosecant. Notice all the ones on the right hand side have the negatives. All the ones on the left hand side have positive answers. And of course underneath are just the chain rule versions of them. Now, there are two other rules that we can figure out. These require us to make a substitution. I hope you remember that tangent x is the same thing as sine x over cosine x with a dx. And now, if you were to use u substitution, let u equals to cosine x, notice that du dx is negative sine x, or dx is just du over negative sine x. So we can replace this with, I guess that's sine x over u, and then my dx becomes du over negative sine x. How convenient those signs then divide out. I'll take out the negative, and you're left with the integral of 1 over u du, and that just equals to the natural log of u. And I'm going to skip a step and just replace u with cosine x plus c. Okay. And you can do the same thing for cotangent. That's just cosine x over sine x dx. This time I'll do the same thing with letting u equals to sine x. Du dx becomes cosine x. So dx equals to du over cosine x. Making that substitution now, cos x over u. The dx becomes du over cos x. Yes, you'll see in this case it's just 1 over u du, and that's the natural log of the absolute value of sine x, and then plus c. And that's why you have these two formulas here as well, and I think you should memorize those too. Okay, I don't think you want to spend time using u substitution every single time to get that. So with those in mind, I think we can now go ahead and do all of these examples. So the first one I'm thinking, that's just negative 3 as a constant. I can pull that out. And I'm asked to integrate sine x dx, and of course that's just negative cos x, and then don't forget the plus c. So putting the two negatives together, there we have it. Alright, number 4, you see it's cosine of a function, so hint, 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 perhaps you have to let u equal to something. I would suggest pi t. Du dx, of course, is just, my mistake, du dt equals to pi, and so therefore dt equals to du over pi, which means that I can rewrite this as cos u with du over pi, which means I can take out the 1 over pi and ask you to actually just integrate cos u, and that equals to sine. And once again, I'm going to skip a step, and I'm going to replace u with pi t, and of course the plus c. Okay. Now I think all of these you can use u substitution, so I don't think I really need to teach you too much more. You can actually try these on your own. Okay? So take the time now, try them on your own, then come back and double check the answers. Notice how this simplifies nicely into just the integration of secant u du, and that of course is just tangent of u, and once again I'm going to replace u with y cubed plus c. And don't forget that 1/3 in front. That's what I just forgot to do here. Right? Secant tangent. Where have we seen that before? So I'll probably let the stuff in the bracket equal to u. Secant u tangent u du over 2. Integration of secant u tangent u. Hello secant. So once again I will replace the u. There's your answer for number 6. 7's a bit interesting. Cosine. Notice sine's in the bottom with a square, so I'm thinking I'm going to let u equals to sine of 5x, the entire thing, because when I take its derivative du dx, I get cosine 5x, and yes, I get an extra factor of 5, but it's a constant, so I don't have to worry too much about that. Dx, of course, is just du over 5 cos 5x. Time for me to make my substitutions. U squared dx is now du over 5 cos 5x. Beautiful. The 1/5 I'll pull out. Don't think that the integral of 1 over u squared is ln u squared. It's not. This is just power rule. So 1 over 5, the integral of u to the negative 2, add 1 to the exponent, divide by the new exponent, plus c, make the replacement. That must be just a sine 5x in the denominator. Good. And if you really wanted to change that from 1 over sine, you could have written this as just cosecant 5x plus c. That works too. Last one. Always thinking about what do you want to let equal to u, and hopefully one of those things equals something else in your function. So I'm thinking I see tangent. I know that du dx equals to secant squared d theta. My fault, not dx. So used to doing dx. So d theta equals to du over secant squared. Making the substitution now. Secant squared theta over u. Du over secant squared theta. Oh, hello 1 over u again. That's, of course, the natural log of the absolute value of u. Plus c. Cool. No questions? Nice. If you do have questions, ask me in class. Turn the page. So 2 more examples today. This time I want you to integrate tangent squared x, and whenever you have something like tangent squared or sine squared, that gets a little tricky. But it's actually quite simple to integrate correctly if you remember those Pythagorean identities. Right? Sine squared, cosine squared equals to 1. If I want to divide each term by cosine squared, I get this. And that will come in handy for my question here, because tangent squared x, if I take that, is just equal to secant squared x, and I can take the positive 1 and move it to the other side. So really the integration of tangent squared x is the same thing as secant squared x minus 1, and this is nice because the integration of secant squared just happens to be tangent x. The integration of negative 1 is just x, and don't forget indefinite integral, so plus c. So sometimes a quick trick like this makes your life a lot simpler. Okay, assignment or example number 10, asking you to find the area bounded by these two curves. And I'm hoping that you can use your calculator, because I can't figure out the intersection point of these two curves by algebra. But I know 2 cosine x probably looks something like this. Whee! Half tangent x probably looks something like this. Whee! So our goal is to figure out the intersection point and then be able to find the area bounded by this region, which I'm going to color in with green. So I'll need my calculator. You should bring out yours too. Remember, you should always be in radian mode. Radian mode. Radian mode. Good. Radian mode. Radian. Time to graph. I'll put in, 2 cos x. 1/2 tangent x. I will actually change my window to only go from 0 to pi over 2. And my y value, sure. Let's see what happens. Here is 2 cos x. Here is half tangent x. And let's go ahead and find the intersection point. Second calc, intersect with number 5, first curve, second curve. And remember, our goal is to find the intersection point to 3 decimal places, 1.082. Nice. So 1.82. 1.082. 1.082. With a y value of 0.939. Okay. So we found the intersection point. Our goal is to find the area bounded by this. Hopefully you remember how to find the area. And we take little rectangles. Notice the height of the rectangle is just the difference between the higher function minus the lower function. So the area, hopefully you remember, is equal to the integral from 0 to 1.082. The higher function of 2 cos x. Take away the lower function of half tangent x. And then don't forget your dx. And you cannot do this by hand, so hello calculator one more time. Okay, I would say, how about using the fn int feature, number 9, oops, not here, in the calculation menu. I will take 2 cos x minus half tangent x. Don't forget comma x, comma 0, comma 1.082, your limits. 1.388. Okay, there you have it. So, taught you the basics of doing the integrals of trig functions, and now you should be able to apply it to every single possible integration application that we've learned so far. Alright, I hope this was good. Time to do some work.